Hi, welcome back to Bio 6612. We're going to get started this week talking about logistic regression. So today we're going to cover measures of association for 2x2 tables, modeling binary outcomes, and interpreting logistic regression coefficients in a setting with one binary variable. So we already saw linear regression, we're very familiar with, and in linear regression the outcome being modeled is continuous. And the data, or the error distribution at least, is considered normal. Another regression type is Poisson regression, which we'll learn about later in the semester. And with Poisson regression, you model count data and assume a Poisson data distribution or a quasi-Poisson data distribution to relax some of the assumptions about your variance, which we'll also learn about later. For a Cox proportional hazards regression, you're modeling survival data or time to event data. And for that, you can assume an exponential or Weibull distribution or a non-parametric form in general, which we will not get to this semester. And then there's logistic regression, which many of you probably have already used in practical settings. And with logistic regression, you're modeling a binary outcome, and you assume a Bernoulli or a binomial distribution. So there's also a couple other types of logistic regression for when you have more than two categories for categorical data. There's polynomist logistic regression for nominal or non-ordered categorical data, and ordinal logistic regression for ordered categorical outcomes. So as we've learned over the last couple of weeks, GLM theory tells us which link functions to use based on what data distribution we choose. And generally, for the normal distribution, we use the identity link. For the Poisson distribution, we use the log link. And for the Bernoulli or the binomial distributions, we use the logit link, which is the log of mu over 1 minus mu. And as a reminder, mu here is just the expectation that yi equals 1. As a reminder, mu here is equal to the expectation of yi. So that brings us to logistic regression, which we'll focus on for the next couple weeks. And logistic regression is used to model the association between a binary outcome where yi can equal 1 or 0, and one or more explanatory variables that can be binary as well, or categorical, or continuous. And there are tons of examples of what binary outcomes can be. I have a couple listed here, and these include yes, no disease, Democrat, Republican, and many more. So in many epidemiological studies, we're interested in determining if a particular exposure, also called a covariate or risk factor, is related to the development of a particular disease or outcome of interest. In this framework, we assume both a binary outcome and a binary predictor or exposure of interest. And these 2x2 tables are really the precursors to logistic regression. The way that they're generally set up is you have your outcome or response, which would be maybe disease or no disease, and your A. And this part of the table is a number that represents the number of people who have the outcome of interest, say a particular disease, and are also exposed to the risk factor of interest. B are the people who don't have the disease but were exposed. C are the people who have disease but were not exposed. And D are the people who both do not have the disease and were not exposed. So there are a lot of different measures of association you can calculate for 2x2 tables. Generally what we're doing here is we're trying to find measures that quantify the strength of association between the exposure of interest and the disease. The two that I'm going to talk about are relative risk, which is also called the risk ratio, and the odds ratio, where the odds is equal to the probability of disease over the 1 minus the probability of disease. And an important thing to note, which we will reiterate later in the semester, is that the odds ratio is appropriate for cohort, cross-sectional, and case control studies, but the risk ratio is not appropriate for case control studies. So let X be the outcome when you're rolling a fair six-sided die. So the probability that you roll a 1 is 1/6, and the probability that you don't roll a 1 is 5/6. You would then say that the odds of rolling a 1 are equal to the probability of rolling 1 over the probability of not rolling a 1, which is 1 in 5, or 1 to 5 odds. And similarly, the odds of not rolling a 1 are the probability of not rolling 1 divided by the probability of rolling a 1. You would say the odds are 5 to 1. And what this means practically is that if you were to bet on the outcome of X equals 1, then you have 1 chance to win and 5 chances to lose. Consider an observational study where researchers are interested in quantifying the relationship between lung cancer and drinking status. And so they have it divided up. So here are people who have the drinking status is divided as a binary variable into heavy drinkers and non-drinkers. Then there are people who got lung cancer and did not get lung cancer. And you see the number of people in each of these cells. So if you wanted to calculate the risk ratio, this is given by the probability that you have disease given that you were exposed over the probability that you have disease given that you were not exposed. And so the probability that you have disease given that you were exposed is the people who have lung cancer and are heavy drinkers. So that's going to be 33 divided by the total number of people who were exposed. So 33 plus 1607. And then the probability that you have disease given you were not exposed is the number of people who have disease but were not exposed, that's 27, divided the total number by the total of number of people who were not exposed, which is 27 plus 2,273. Then the risk ratio is calculated by, then the odds ratio is calculated, the odds of having disease given you were exposed over the odds of disease given that you were not exposed. And this is actually, it should be a 2 right here, not a 1. And there's a simpler way of calculating that using the tables, which is you can just take cell A, which is here, times cell D, which is here, and divide by cell B times cell C. So for this lung cancer and drinking example, the risk ratio is 1.71. And values of the risk ratio can take on the range in 0 to infinity, where a risk ratio of 1 indicates no association between the exposure and outcome. Risk ratio of greater than 1 indicates positive association, where exposure is related to disease, and a risk ratio of less than 1 indicates negative association. The exposure is related to lack of disease or reduced risk of disease. And the way you would interpret this risk ratio is that the risk of disease, or lung cancer in this case, in the heavy drinking group is 1.7 times the risk of lung cancer in the unexposed group. The odds ratio for this example is 1.67. And odds ratios can also take on values in the range from 0 to infinity, where an odds ratio of 1 indicates no association, greater than 1 indicates positive association, and less than 1 indicates negative association. And the interpretation of the odds ratio in this example is that the odds of disease in the heavy drinking group are 1.67 times the odds of disease in the non-drinking group. So more generally, what is a good approach to modeling binary outcomes? Well, generally, we want to be able to include more covariates than just one binary covariate. And we want to be able to include covariates that are continuous and categorical as well. So as you might expect, regression is going to be the answer to that. And in general, we want to model the probability of an event occurring given a set of covariates, which I write as pi equals the probability of y equals 1 given x. And some potential options are linear regression. We discussed this before. It's not a great option, but in this case, you would be modeling that probability is an outcome, and then you'd have a set of betas and coefficients. And this implies that your pi can be in the range from negative infinity to infinity, which we know isn't true because probabilities can only take on values in the set 0 to 1. Instead, we can model the relative risk by modeling the log of the probabilities. And this is what's called a multiplicative model with a log link. This is a little bit better because it only assumes that pi can be in the range from 0 to infinity, because if you exponentiate this to get pi equals e to the x beta, this can only be a positive value, so you no longer have the negative values to worry about. Or finally, you can model the log of the odds, or also called the logit of the probability, which you've seen already and is given here. And this is what ends up working out great, because now we actually have pi in a range from 0 to 1. So, and the inverse of that is that the log odds has a range from negative infinity to infinity, which is why it matches up with your x beta values, which can be from negative infinity to infinity as well. So if we model the log odds, when we back transform, this constrains pi to be between 0 and 1. And just, it's good to sort of work through the algebra to prove this to yourself. And then when you go about doing that is you start with the model, the log pi over 1 minus pi equals, I'm going to write x beta, which is the matrix notation for beta 0 plus beta 1 x1 plus beta 2 x2, etc., just because it's a little bit easier than writing that out every time. You're going to exponentiate that to get pi over 1 minus pi equals e to the x beta. Multiply by both sides to get pi equals e to the x beta times 1 minus pi. Distribute that pi and move it to the other side. You get pi times 1 plus e to the x beta equals x beta. Divide by the e to x beta. I'm going to move this over here to get pi equals e to the x beta over 1 plus e to the x beta. And cool, that looks just like what we have in this first part of the equation here. To get to this second piece, all you have to do is move that. So e to the x beta, you can move that on the top part in the numerator there. You can move that in the bottom by saying that's equal to e to the negative x beta times 1 plus e to the x beta. And then by distributing this negative into what's in the parentheses there, you end up with pi equals 1 plus e to the negative x beta. And these two forms here are both equivalent. They just, sometimes one can be easier to work with than the other. And so it's good to know how to go between both. That brings us to the form of the logistic regression model. So for a given subject in a study, we are interested in modeling pi I equals the probability that yi equals 1 given a set of covariates xi, where yi can take on the value 0 or 1. The logistic regression model then takes the form logit pi I, which is equal to log pi I over 1 minus pi I, or more specifically, log the probability that y equals 1 given xi over the 1 minus the probability that yi equals 1 given xi. And on the right-hand side, that's equal to the sum of the betas times the covariates for that subject. And it's called logistic regression because the log of the odds is known as the logit, or logistic transformation of pi. So we're going to talk more about interpreting parameters in later lectures as well. But for now, I'm going to start with an example with just one binary predictor. And I'll use the lung cancer and drinking status example from earlier. This model, if you model that data as a logistic regression model, looks like this, where you only have an intercept and beta 1 times 1 xi, where xi is just a covariate that can be either a 0 if the subject I is a non-drinker, or a 1 if subject I is a heavy drinker. And yi can take on values of 1 if subject I has lung cancer, or 0 if they do not. And then pi I is the probability that that subject I has lung cancer given their set of covariates. So the way that you interpret the intercept here is the intercept is just the value of the outcome when xi is equal to 0. You get that by, if you plug in x equals 0, this cancels out, and then you have beta 0 equals the logit of pi. So in the context of this particular example, then beta 0 is the log odds of lung cancer for a non-drinker. Of course, you can exponentiate both sides to get pi I over 1 minus pi I, which is the odds of lung cancer, equals e to the beta 0. So by exponentiating beta 0, you can interpret that as the odds of lung cancer for a non-drinker. We interpret beta 1 in a similar fashion. So when xi equals 1, you can plug that into this equation and get beta 0 plus beta 1 on the right-hand side and this expression on the left-hand side. And when xi equals 0, you plug that into this equation to get this on the left-hand side and just beta 0 on the right-hand side. And then you can use this to solve for beta 1 by saying, okay, the first thing, beta 0 plus beta 1. So on the left-hand side, you get beta 1, and on the right-hand side, you get this expression where you have the log odds of lung cancer for somebody who is a heavy drinker minus the log odds of lung cancer for somebody who is a non-drinker. And this is also known as the odds ratio for comparing heavy drinkers to non-drinkers. Sorry, the log odds ratio. And if you want the odds ratio, you can just exponentiate B1 and exponentiate that side to get the odds ratio. So in summary, e to the B1 is just the odds ratio of cancer comparing the drinking group to the non-drinking group. In general, for logistic regression, and more generally for generalized linear models, the beta is the change in the outcome, g of the expectation of yi for a 1-unit change in x. In logistic regression, this is interpreted as the expected change in the natural logarithm of the odds. And you can exponentiate your beta to get the odds ratio. And so next lecture, we're going to talk about how you actually estimate your beta values, which you estimate using the maximum likelihood estimator of given your observed data.